may say, does this refresh your memory?
Is that what you have in mind?
Yeah, that's
Yes.
And is that the different size rectangle you wanted?
No, I want that one.
You want that one?
Those are infinitely many, and they smallest one. One point.
There's something slightly wrong with this.
Yeah, don't
That's
you?
a golden rectangle to begin with.
One, it has to be a golden rectangle. What do you mean by golden rectangle?
Yeah.
The ratio of the sides
So
is
it's divided by the square root of 5 plus 1 divided by 2.
I.e. 1.6 feet.
Yeah,
golden.
and there's
Came
a
up
point that
yesterday
isn't
in
covered by a square.
There's something else slightly wrong with this, just a tiny thing.
Yeah, one
So
point.
there are two equal.
There are two equal squares in the middle. We wanted all the squares to be different sizes.
No, but if we went for forever,
What do you mean forever? Tell me how
oh, I
to do
just
it.
keep putting more and more in, and there's, at any point, there's nothing.
That sounds great, but could you, I'm being very nitpicky.
Yeah.
Where do you want me to go on and on forever?
Inside.
There's always a golden rectangle missing that you haven't covered yet, and so I want to cover it in the same way.
So are you saying take one of the two congruent squares and,
So after you've cut off one square, there's a golden rectangle left.
and then just simply
Then
repeat
do
the
the same
process?
thing to that. That was my
They
idea.
actually are
Remove that line
Right.
that made them
You
two
don't ever
identical
stop.
squares and do the process again. Terrific. So you've now solved the problem.
No,
We have now
well,
tiled
no,
a particular rectangle
no, you haven't.
with an infinite number
No, you haven't.
of non-congruent squares.
Actually, it's
No, you
it's
haven't.
precisely, I mean, it's rational. I mean, it's not precisely
Yeah,
golden
the-
section.
yeah.
It's rational. I mean, it's
You mean our particular picture?
yes. I mean,
Yeah.
it's not approximately golden.
You're quite right. It's actually fine.
Well, I mean, I just have trouble drawing infinitesimals, so.
Yeah.
But if it were exactly,
If it were
exactly,
exactly.
you would continue infinitely. I mean, infinitely far.
And it wouldn't cover the whole square.
Why
We're
not?
missing the point of convergence there. It doesn't get covered by any of the squares.
Can you call a point I mean, square of size 0?
Do we get to that point?
Question, are we going to allow squares of size 0? Because if we do, we could just do a pretty general sprinkle here.
No, because they'd be
No,
the
no,
same
just
size.
one of it. One of it.
Only one of them. If you were all, we tend to do this with
Each of the zero sizes twice as large as the other.
This is a problem that we do with 8 to 10-year-olds over 10 one-hour periods, and this is exactly the sort of thing that comes up. The golden mean rectangle comes up very, very early on, surprisingly, and just this sort of discussion comes up where you can go in many directions. Could you have a square of size 0? What does that mean? Should you go on forever? What does it mean to go on forever? What about convergence for 8 to 10-year-olds? Well, for us, that's a real issue. Is the problem now over? Not for you, because
Well,
what's wrong?
I mean, there's several things we need to do. First of all, the finite case is interesting. Let's do the finite. Let's not just skip over it for the infinite.
So you're saying, look, infinite is all very well, but
yeah.
our original question was, can you tile a rectangle with non-congruent squares? There's something wrong with the question. Something fruitfully wrong with it. What's wrong with that question?
Is it any rectangle or
Right. The
particular one?
question is deeply ambiguous, which I think is the best kind of question to ask in a math circle. Half of math, as you all know, is reformulating a question so you can answer it. Bring it over to the streetlight. Ask a question in a vague, ambiguous, wrong way, and let the students work on it to reformulate it. We've gotten 2 reformulations. 1, I want a 10 by 10 with a smiley face in it. 2, well, I can do it with one particular rectangle, the golden mean rectangle, and then the tiling is infinite, and it's got a few problems connected with it. Terrific. What direction do we go in now? Should we go in your direction?
Sure, let's do that.
What do you mean 10 by 10? Why'd you choose 10 by 10?
Because it was a square. I only had one square to tile it with.
Can you tile a square with non-congruent squares?
Yes.
An infinite number?
No 2 of those are congruent.
No 2 of which are congruent.
That one thing.
We've now gotten the lower and the upper bounds for the problem.
So this is what we had. We'll make it be a square, in which case one square does it, and we're finished. We make it be golden rectangle, in which case infinite number of squares does
No,
it.
it doesn't do it.
So how about avoiding the slither and saying by rectangle we do not mean square, and we really
So you want a finite number. We know we can do it with 1. We know we can do it with an infinite number. In the
Sort
two
of.
special cases, golden rectangle and only 10 by 10, I guess.
Right.
So if you're finite,
And
you
it's
maybe.
only 10 by 10?
No, any
Oh,
whole square.
any.
Yes, pi by pi square would do.
Oh, okay. So you're saying the one tiling works with any square? Well, yes. Great. Okay. I just wondered why you chose 10 by
Deep
10.
result there, you know.
Yeah, I saw. Yes.
It strikes me that if you require that there really be 2 distinct squares in your tilings, so that they can be different sizes, the square could be kind of hard.
Right. If the tiling.
Require ends more than 1.
So if the question had been, can you tile a rectangle with 2 non-congruent squares? With a rectangle, a non-square rectangle.
Well, okay. Well, say you do 2 by 1, and your first intuition is to cut off half the
Right.
square, and then you get this square, and it can't be that you can't tile it with the same size as the other piece, and so you got to tile this square with 1 and 1 square, and it's starting to look hard.
Good.
They could also fit like at the shift like this. Like this.
Ah, what if they were slightly skewed to one another, slightly off? Rather like your picture here,
Or like
which
that.
might be the beginning of some finite possible tiling. Okay, stop for a minute, back up, and think about this being a math circle class with 8 to 10-year-olds. It's been tremendously exciting. You've caught their attention. They've now put their egos and their outside life outside the door. They're obsessed with the problem, but in many directions. What should you do? Focus into a few or one direction, putting the others on the shelf? How do you keep some things on hold while others are going on? How do you not neglect the people who haven't said anything? How do you bring them into the conversation? How do you keep the idea of this 2 squares and what happens next alive while thinking about, well, can you do a tiling with non-congruent squares in a square with more than 1 but fewer than an infinite number? Maybe it's not possible. Maybe with a square you can only have a 1 tiling.
And there's a further question, which happens only when you actually have a kid group rather than a grown-up group, which is the vocabulary used by some is incomprehensible to others. And so you have to do a constant running translation, like the UN, where you're trying to think, what is the word for mutually assured destruction?
So far in this conversation, phi 1 plus the square root of 5 over 2 have come up, infinite tiling. Some of these terms might be confusing to a kid. What we like to do is have them invent their own names for things. And so this is Joe's rectangle or Anne's way of tiling. If at the end they've come up with a theorem of Gauss's, you might want to warn them before they go out into the outside world. Other people tend not to call it Anne's theorem, but Gauss's. But that's just a mere technicality. There was a hand, yes?
With kids, do you get what might be called covering rather than a tiling? Are they going to come up with things that overlap?
Yes.
I would assume so.
Indeed. In fact, you've all zipped past a lot of wonderful kid suggestions, not only overlapping, but can we put the tiles in sideways? Could we put them some in vertically? What about grout? I mean, if you're tiling, what's wrong with using some grout?
That's
here and there?
interesting. That's nice.
Do the tiles, could they be almost square? Could you trim off an edge of one?
You've got to forgive us. We just don't have their skills.
You have to get yourself back into that kid mentality where everything goes, not just anything goes.
Yeah, another process question. I know if this were a real circle and I were involved and I got an idea, I would start ignoring what's going on here and working on my idea. And I don't know if that's bad or not, but I would, if I try to jump back into the conversation later, I've missed.
Yeah.
It's a really good point.
Should you try and get kids not to do that? Or
No.
what do you suggest?
No, get them to do it.
This
Good
is my
reason.
idea.
Good reason for
Heck with
not
the rest
letting a
of you.
group get bigger than 10.
Mm-hmm.
Because that way you can have a kind of pause where people are checking things out and then people come back. But by having these tables, you're in a certain position of anonymity. For example, I bet we could keep track and only about half the people in the room will actually talk. Whereas if there are 8 people in a room, there is a social requirement. You don't sit at the dinner table and work on a problem.
But also, if they're sitting in a semicircle, and we do try to have our math circles be math semicircles, they're seeing one another and responding to one another. And when one person's absorbed in a problem, and you've caught on that he or she is out of the conversation, has been out for 5 minutes, ask one of the other children to fill him or her in. Anne, could you catch Bill up with what's been going on? And now, Bill, what was your idea? What have you been working on? It's when someone says, when a kid says, well, I have an idea, but no, forget it, it's not worth it. That's a really important point because it's usually very worth it. Especially if the idea is crazy, off the wall, it often helps. You say, go on, be daring, just say anything. If they're too cautious, say something stupid yourself. Say something off the wall, say something wrong, and let them correct you. Because that puts them in a position of power.
The idea that you can take risks, intellectual risks as well as social risks, is, I mean, what makes mathematics move forward is somebody thinking something that they had not read in a textbook.
Quick summary of where we are. What about, we're now thinking about finite tilings. We've got a tiling with one of a square with itself, an infinite tiling of the golden mean rectangle. Are there finite tilings of more than one tile with which rectangles, with perhaps a square? And I think I'd seen marks. Oh, yeah, okay. Yes.
I was wondering how long does it take for them to realize that you don't have to stick to integer side lengths for the squares or rational numbers? Do they see that half by half is okay?
It varies class by class because of personalities in the class. Some people will come up with quite daring, advanced, off-the-wall, slightly skewed suggestions, which you can lead back toward what you see as the fall line. Ellen, well, your image of the Sherpa, I think, is a very good one.
Yeah, I mean, ideally, what you do is you let the ideas fly, and when things crunch to a stop, then you are the person who has brought the supplies up the mountain, and you put down another knapsack that people can look in. I mean, that you're not directing the way they go. You may say, don't step in that crevasse.
But
If you know something is infinite regress, you might want to say something. But it really is done in the conversation between the kids.
So that they feel that they're empowered, that they're doing the math because that's what you want.
Every once in a while, at the beginning of a term, somebody will say, are we allowed to ...
Yes.
Yes.
And would you say, yes?
It's
You are allowed to, you are encouraged to, if it does not involve profanity or hitting people. It's pretty much any idea you have, we would like to have going to the top.
And let false conjectures run because they'll self-correct. Most conjectures are false after all.
We talked about the smartest kid knows everything in math. What about sort of the opposite, which comes up? And the typical thing that I find is the kid who whines, it's impossible, and then
Yes. I have a feeling precisely that is going to come up in 10 minutes. Was that a...
You asked a question that I'm eager to hear the answer to. That is, with all these different suggestions going, how do you keep them all alive without dying, without completely vaporizing the conversation?
Really good question.
Well, I didn't ask.
What I do is I make quick summaries along the way more often than I would naturally tend to because I've got 8, 10, 12 different personae in the room. So I'll say, let's see, where were we? Okay, we have the infinite tiling, we have the one tiling. We're trying to figure out if we can with a finite number. Oh yeah, we had that idea here, which we've abandoned. We should get back to that, shouldn't we? And I guess as any size square, we should think about, can it be done with more than one and fewer than an infinite number? Is that roughly where we are? And then one of them will say, no, you forgot such and such. And then you say, well, okay, which one do you want to work on? And let them take over so you become their secretary.
Sure.
Every room in which you do a math circle should have as many blackboards as possible so that you can keep little parenthetical corners full of all sorts of different things. You don't erase anything, even if you think it's a truly foolish idea, because it's very surprising how often something comes around this way and turns out to be good.
A related problem is class tends to end after an hour, and then they are gone for a week and then come back, and things are usually up in the air at the end of the week. Are they going to remember where up in the air they were? You could ask them to email one another, or have each one be a secretary each week, a different one, and summarize the class for everyone else. When they come back the next week, you say, I forgot. Where were we? What happened last week? What was it we got stuck on? And eventually, it feels like an hour, it's usually a minute.
This is another parenthetical remark. The more they are doing, the more they think that you were the only person who has forgotten what was going on, and they explain it to you, which is very nice and good for one's character to say, oh,
When you become their nice but slightly dumb friend at the board, that's ideal. So, where were we?
I think people are avoiding this problem.
What do you want to do now? Yes.
Impossible.
Now, maybe it's important that the problem can't be done with a finite number, because it's not just the problems that can be, it's the problems that can't be that tell you something about the world. And I think mathematics comes in two flavors, chocolate and vanilla. And the vanilla is you listen to the world passively. You listen to the problem and let the problem tell you something. And the problem is saying, can't be done. We've gotten the infinite case. Come on, how much more do you want? We've gotten the one finite case. It just clearly, there's something intrinsically difficult here. That's one half of math. The other
That is
half,
a big shock to kids, by the way, who know that every problem has a solution and it's in the teacher's manual. So there's a, look, why should I be breaking my head attempting to do this when all I have to do is ask the teacher? And if I whine enough, she'll tell me.
the other half is imposing your will.
In the beginning, you didn't mention that it has to be finite.
No, we didn't
And
mention.
that's
That's
why
right.
we went in that direction.
That's why posing the question ambiguously, badly, underposing it. So the other half of mathematics is imposing your will on the world, saying, I want this thing tiled with a finite number greater than 1, and I'm going to do it. We're going to do it. I don't care what the world is telling me. Let that dialogue loose between what is and what you want. There's a wonderful book by Imre Lakatos called Proofs and Refutations about the Euler characteristic, where he says, try to prove and disprove at the same time. Something's going to come out of this. Well, maybe nothing. As Jim was saying yesterday, sometimes you run a math circle class and nothing comes out of it. You just hit a problem that can't be done. With kids, it often helps to say, when you get to a really hard part, when they're stuck, to say, well, you know, we may have reached the limits of human capacity here. This may just be a problem that humans can't do. There are undecidable problems. This may be one. Right? It's 10 of 11 on a March morning in Arizona. We've hit the wall here.
Never.
I could swear there was a cover of Scientific American with
You have outside knowledge.
a size of one that did work. So another question I would have is, if there is one that can be done, what is the nature of such a beast?
Great. What is the nature of such a beast? Let's approach
Well,
it. Shall we pick up where we left
Well,
off?
you know for
What
sure,
now?
it's a rectangle. So we're starting correctly. And if you have this image of a rectangle, this is Joe rectangle.
We mean a non-square rectangle.
A non-square
Yeah.
rectangle, and we've got 2 squares in it. Next step.
I'm tempted to try with the largest possible square that you can build
That was
out
your
of what's
suggestion. Put in
remaining.
the largest possible.
Yeah, so we
and
got the
then-
largest possible.
And then put in another. And your suggestion was to make it half the size of the original.
Oh, the largest possible.
No.
Well, actually, my suggestion would have been 0.6, because I was trying to stick in golden rectangles in there and then cover it, and then put another one in, cover it, but at that point, I thought you were allowed to have infinite.
Yeah, so
But not, yeah.
Nice
we're there.
point. So,
Let,
yes.
I would try to make a pattern of what the things would look like without figuring out the sizes, and then stop it and try to figure out the sizes at the end.
he's read the magazine
That's a
too.
very sophisticated thing to do. Could you say it again to an 8-year-old?
I mean, you draw this little rectangle square that she had there before,
Yep.
and then change it.
What do you mean change it?
And then change the original rectangle by erasing the right-hand line and making that the right-hand line there.
So assume the solution and alter it. Yeah, you try to make a square that would fit whatever pattern you're trying to build.
Instead of working from outside in, work from inside out. That's nice, like analytic and synthetic. Yes?
I have a whole bunch of tiles on my table. I don't have a rectangle, I just try to put them together so that...
Again, take your pieces, take your non-congruent squares, and mess around with
Turn them
it.
into a rectangle.
I think I want to think of the smallest because there is if there are finite number of squares, there should be smallest one. So I would rather consider the smallest and how it fits around. I mean, how other ones around it or on one side of it or whatever. Probably it must be that it must be covered. I mean, it must be neighbored by 4 other squares on 4 sides. Like that.
Okay, can I just summarize? Here's where we are. We have the go from inside out instead of outside in strategy, build up to a rectangle from a series of non-congruent squares, or there must be, am I paraphrasing you correctly, there must be 4, what do you mean?
I mean, consider the smallest possible square. Like call it 1 by 1, for example.
You mean a square inside our rectangle?
Yes. Assume that such a pattern does exist.
Where would you like it?
Now we have to
out in the middle,
it probably can't
out
be
away
on the
from us.
side. It must be inside.
We'll put them here.
Somewhere here, yes. And
There
then
are too many cooks in this world.
I guess the only way to fit other.
Why can't it be on the side?
Why can't it
Have a rectangle that has it on.
Thank you. Then you won't be able to resize around it.
Have a rectangle that has it on.
I haven't done enough for everyone. This is the only way basically to do share with this. But then because if it is on the side, 4 squares. No.
And I just got one in the back of it.
So there would be no way to fill in this.
Your suggestion was think about the smallest square. And then where did the number 4 come in?
Sorry?
You said 4. Something about 4.
Yes, like
That's 4 sides.
The other question, this is what we're discussing right now. Like, where is it located? Can it be in the corner? Can it be
Good
on the
question.
side?
Okay, we're now half an hour in, and the idea has come up. There has to be if it's a finite tiling, there's got to be a smallest square. Could the smallest square be in a corner?
No.
Why can't it?
Because then you won't be able to fill the rest.
Could you explain in detail?
Here is the smallest square,
Yeah, if it isn't.
and it is in a corner. Tell me what goes wrong.
Okay, look at the one
Because
next to
then
it.
you try to cover the space, for example, just below it. And then that should be a bigger size, and therefore it should stick a little bit to the left. Yes. And then now consider the space just to the left of the small, and you won't be able to cover that.
Great, because you get a
Because that is
square
the smallest.
congruent to the one that's already there. The kids tend to call this the corridor problem. And once they notice the corridor problem, the chain of reasoning goes like this. If it's a finite tiling, there has to be a smallest square. If the smallest square is in the corner, there's a corridor problem. Can't be done. The problem can't be done. We've just proven it can't be done.
No, you can't.
Oh, if the smallest square is in the corner. So modify what I just said. There has to be a smallest square. If it's in the corner, then it can't be done.
So therefore,
What'd you say?
Therefore, it must be either on the side or inside.
Good. So now it has to be either on a side, not in a corner, or inside.
inside.
What about on a side?
Probably same.
Get a corridor.
What's wrong with being on the side?
We get a corridor.
We get a corridor.
Same thing.
Good.
Same
Looking
thing.
bad, isn't it? Would you like to take a vote at this point? Do mathematics by
Now
democratically.
yeah,
How many people
we'll do
feel
the
this?
same thing.
That the answer is it cannot be done with a finite number of tiles in a rectangle, a finite number of non-congruent squares. 1 vote from Craig.
No, we
2
But
votes.
this is we're voting that it cannot.
How many people think it cannot be done?
it is killed by the corridor problem.
Terrific, terrific. How many people feel it can be done? How many people are not going to vote? You're voting.
Who's copying your vote?
Okay. This is where we tend to reach in about the 3rd week, the 3rd hour. And at this point, something interesting happens in a math circle called frustration.
No,
Just
something
teasing
that
us.
you
Come
guys
on,
would
quit.
suffer from.
Tell us the answer. I mean, come on. Either
Actually,
can or
they're a little more grown up. They say, assure us that there is an answer. And I think that's very reasonable. Life is short, and you really do not want to keep hitting your head against the same brick. So the question is, can we assure you that there is an answer?
And I tend to say at that point, well, there probably is, but I'm not sure that we will ever know it. I mean, there are undecidable problems. I mean, it probably can or can't be tiled. I'm not sure I know of a third alternative. Or it might be both can and can't. I can't picture that. But,
Because one of the things that we have in mind is, in this fast-moving world, to change the threshold of frustration. I've taught 4-year-olds who are frustrated after 4 seconds. Very few problems can be solved in 4 seconds. Teenagers won't even go into a room which contains a problem which can't be answered by looking it up on your cell phone. So you drag out, by whatever means you have, the interest in the subject or the interest in the group until people can say, I've just had a new idea.
So raise the level of the threshold of frustration, partially by having a lot of things going on at once. Dave.
So this makes me want to describe one of the evaluation tools we developed in the Bay Area thing. It's a concentration system. Before students start doing math circles, we take the teachers who are there, we send them into back to quizzes to the classes, and got some puzzle type problems, and work on these problems. You can turn in these problems, each of the times when they're turned in, and they keep track of how long the students work on it, and tell us that down. And then we do it at the end of the math circle. Then we correlate those who have been in math circles, who have not, or try to test until we get people to spend longer thinking and scratching their heads on a problem.
It's a nice way of actually having a measure, a kind of a measure. We've certainly found, but this is only anecdotal since we don't believe in statistics, that in a group, a small group, 12 is large, the group dynamic, the people reinforcing one another, saying, oh, you're right, I just don't see it either. The either is important. So you feel you've got an ally in your frustration. And that allows people to go a little further. And when there are several lines of thought going, okay, that line has been blocked off. We can't get the smallest square in a corner or on an edge, so it's not looking good. Well, there's still the possibility of being in the middle somewhere. So there's a line of thought to follow. Craig.
Well, I was going to say something about the problem.
Yeah, good.
Well, the reason I'm beginning to think that it's not possible is because if we go back to the idea that you can change a rectangle size to just trying to find an answer, as long as you end up with a golden rectangle, you can put the square into the side by extending it up, or you can put the one on the side. There's something in the middle getting up on the side, I think. So I'm not sure they're really different.
Let's put one in the middle and see. Let me just understand what you mean.
Yeah,
There's the smallest square in the middle.
Yes,
Did you want it punk in the middle or just somewhere
It
floating?
doesn't matter. It's somewhere.
If you extend the 4 sides like this, like like a German cross.
Yeah.
So yeah, exactly.
Now what? Is
Square
that,
in one square.
Yes.
is that what you want?
Yeah, that's exactly what I did. Yes. Then it is possible. I mean, at least locally it is possible.
So there's your 4 around your non-edge smallest.
And there's no corridor.
Okay, now what'd you say?
And there's no corridor.
And there's no corridor so far. On the other hand, we haven't gotten to the edges.
That's right.
Sort of like so locally it is possible, but what happens when you
Get to that.
go further?
What happens when you drift toward the edge? All of a sudden, it's a different kind of problem. We're not talking about boundaries. And you
Oh
know,
yeah, let's get rid of the boundaries. Let's just put squares out until
which
we
is
get
going
something
back
sort
to
of
the
rectangular.
technique of building outward instead of being confined by the original rectangle. But will it keep being lumpy? Or will it ever smooth out?
Depends on how clever we are.
A small square adjusted to the boundary. Squares adjusted to the boundary have finite sizes. Out of these, pick a smaller square and look at its neighbors.
So you're saying the smallest square of all will be not on the boundary, but of the squares on the boundary, pick the smallest of those, look at its neighbors,
That's interesting.
and look to see what the geometry is in that locality. Nice idea. I mean, there are going to be squares on the boundary if the problem is solved, and
There's
one of
gotta
them
be a
will be
square in the corner
smallest.
if it's solved.
What will the neighborhood look like?
It's exactly would be the same situation as if the smallest possible square was on the boundary.
Which is making it sound as if it's not going to work.
No, but it's not impossible now, because you can fill in the corridor with smaller squares.
Exactly.
You have
No, I mean, corridor goes out of the boundary. Corridor doesn't touch the boundary. And you can, theoretically, you can fill it with smaller squares.
Except that if that's the smallest one on the boundary, then another one would have to be smaller on the boundary. You would have, if that square is the smallest square on the boundary,
Yeah,
it
that
has,
picture is wrong.
then you can't put another square
That picture can't be.
in the corridor.
That picture can't
No,
be.
I mean, the line she's drawing
No, you
is
can't.
wrong.
Well, no, you
This
cannot do
SB
this,
is
but
the
you can.
smallest, unless it's.
You have to have a corridor just above this.
If I do this square and this square have to be the same size.
Yeah, that's right.
Yes,
So
that's bad.
we can't have, I don't think we can avoid the corridor problem.
No, but
No, we can't.
there should be corridor just above the what you denote as B, just above. I mean, corridor with two straight edges. But this corridor, at least theoretically, can be filled in with smaller squares, smaller than SB, but bigger than S.
So this is not the smallest on the boundary.
It
No, it
is.
is also the boundary. I'm saying you extend upwards. You extend it upwards, both vertical.
Come on.
There we go.
That's what I'm okay. Since this is smallest on the boundary, this one must be larger, and this on the other side must be larger. Assuming, even if it is in corner or not in corner, I don't care. I mean, it should be like this. So there should be some kind of other. And so,
Trouble.
No, that's
what
not.
I'm
No,
saying,
he's not
we
done.
have a
He's not
corridor
done.
in,
Talk.
But now this corridor
Talk.
can be filled in with
things.
something smaller than this, but larger than this. That's what I'm saying.
Okay.
Little
So
tiny.
theoretically, it could be like whatever.
Yep.
That could be S right there.
How many people feel we're on our way? I'm going to ask two questions at once. How many people feel we're on our way toward a proof that it's impossible?
well, but
How many people feel we're on our
this
way
is-
toward a
this
way
is
of
the way
doing
I
it?
think you may be going into dust.
That it's impossible?
make it going forward.
Into
Well,
dust.
let's just all raise our
It's
hand.
looking better and better.
You're asking two questions at once. Let's all raise our hand.
Because, this square here,
There is a feeling among at least a third of
this
you
square here,
that we're
somebody has to go
getting
here.
closer to a proof that it can't be done. How many people feel that we perhaps have a technique here for doing it?
Maybe square on this side is not that big.
Maybe it's 2, 3, 4. Didn't you raise your hand for both? Yeah, good.
I was gonna ask a question.
Yeah, good.
It feels like it's
Can't put anybody on
growing,
this.
and then I wonder
Because if I
where
put
it
anybody
has
on
to
top of
shrink,
this, I gotta
and then the
go.
rate of growth and shrink might be
Is that a problem?
divided by the ratio of the
I mean, we
size.
definitely
Wow.
have a problem.
What a nice idea. That would be too sophisticated an idea, I think, for a 10-year-old. But so you're now looking at rate of growth, both of growth and
That
shrinkage.
was a good,
And say again what you want to do with those two rates.
there.
So what you're saying,
Like,
the problem
it
is already
grows, it
solved.
starts with
Wait,
smaller
it's a little
kids,
harder.
and then also by the rate of growth. So it is, a square has to be more than one square length from the
It's there, it's not
side.
on the corner,
It
it's
starts to get downstairs, it grows, and it gets bigger.
Right.
And then it gets
So
smaller,
we
smaller,
extend
smaller,
it this
and
way and this way.
Now we gotta.
And which way is that taking us? Toward which proof?
No, it's the same.
Theoretically,
What I'm saying is that,
shows that it would exist, but.
okay, consider smallest on the border.
Just
And
a
then,
observation.
it may or may not be.
Wait, what is that?
Just assume for now it's on the border. So this,
Wait, yes, great.
As we're filling it, so I don't think it can be done, but if it can be done, as we're filling this in and we've got an internal space, it would better never be a rectangle. Right, because if we end up with a solution end up with a solution as a rectangle, then we just have a problem all over again.
So we're now coming toward your suggestion that maybe it's with a square that we're going to get a finite non-1 tiling. But probably not for any, but if it's going to work, it's going to be for a square. Is that a hand? Oh, okay. I'm sensitive to hands. Yes.
No, I'm not. Never mind.
Okay.
I think it's.
No, say it. Say
I
it.
think it's clear that it might be true.
Ooh, that's covering your bets.
that there are some rectangles you can do and some rectangles you can't.
Ah, that's the first time that suggestion has come up, sort of a methodological suggestion on a meta level. Maybe there are some you can and some you can't. Golden mean rectangle, we know you can, but with an infinite number. The square, we know you can, but with one.
So this goes to what we were just doing here, which is sort of starting in the middle and building out and seeing whether you can keep on going and fill this up and have them all be question.
With a potential corridor problem here. If this were our 8 to 10-year-old group, we'd probably be in week 5 at this point with a lot of frustration. I mean, you know, an hour-long discussion, 5 weeks in a row, with a lot of ideas having come up, and then imagination decreases. I like your increasing and decreasing series. Imagination is decreasing and frustration is growing. And we may have reached a crossing point. In other words, why not take advantage of our problem, which are the corridors, the L shapes, and make night moves, make L shapes, and do what with them?
Try to tile on L shapes a little bit. So piece on the left of the rectangle that's on the board can be one of the standard L shaped tiles.
Nice idea. Take advantage of the obstruction. If you think about obstruction theory, you analyze what the qualities, what the properties are of your frustration, of the frustration in the problem and the frustration in your thinking. Are we not being imaginative enough? There's something that's been common to every approach so far.
Assume that the squares are lined up with the rectangle. That's one thing.
That's a good point. Often in the first class, kids will say, can we put them in tilted? Oh, sure, why not? And someone will immediately say, look, if you tilt anywhere, you're going to tilt everywhere. And what do you do when you get to the boundary?
How are we going to do it?
You know, I actually think you almost have a solution there.
We're there?
The blue one.
Yeah, we're coming
The
on.
blue one.
The blue one is nearly done, I would say.
Well, yeah, but my guess is that you cannot complete it.
Why not?
Why not? You won't be able to. I mean, you will always hit a situation that you need to use same size.
We're going to keep getting these L shapes.
We got to do numbers in here someplace.
What do you mean?
Well, you know, pictures are good, but our squares aren't really perfectly square.
That's what's been common to everything so far. We've been doing this geometrically. It's a geometric problem. We've been doing it visually.
Yeah, so...
What do you mean numbers?
Well, you know, that's size S1 and that size SB, and that size T and Q, and so T plus Q must be SB, and so on. You know, we got there's numbers. I mean, it's all about adding and subtracting numbers, isn't it?
Fantastic. That would be, we're now in week 7.
What if we took this drawing that's right here with the blue and the black rectangle, and what if the place where it looks dented in the picture was actually lined up? So Ellen,
No.
you know, with the boundary that's to the left of S1, yeah, just make that a straight line down.
You like it out here?
Yeah, great. And then let's just put numbers in so that that's square.
What do you mean put numbers in?
Well, I mean, pick sizes for all the squares.
How about
so
variance?
that one is square.
How about
So
variance?
say this is 5 by 5.
Yeah, 5 by something like that. Or maybe, well, let's start with the littlest one.
Okay.
By the way, is it okay with you to call 5 by 5 what is visually not 5 by 5?
No.
Sure.
Why not?
It's not 5 by 5, you can't move 5 by 5.
Ah, listen carefully. If it's not 5 by 5, you can't call it 5 by 5. Visually, it's not 5 by 5. I have a suggestion. I want to pick up what Amanda's suggesting here and what you said. Why don't you close your eyes and look at it? Taking your idea of numbers. Why don't you picture it? Why don't you picture this rectangle tiled with rectangles? Then close your eyes and let the rectangles wobble until they turn into squares. Whatever wobble means.
Yeah.
And this is
hungry for
where
Jell-O.
the eagle comes down Here's what I mean by wobble.
You mean massage the rectangle?
Just sort of like. I mean, so we could certainly do this with rectangles.
Yeah.
So let's do it with rectangles and then say,
Can we square it up?
were these to be squares? And the use of the condition contrary to fact is not only an important part of Latin grammar, it's a big part of mathematics.
We just tiled a rectangle with 9 non-congruent rectangles.
Why are you erasing that? Who told you to erase that?
Don't worry, it'll come back.
Okay.
But
The
that's
blackboard
ours.
has a memory.
That's ours.
Is this okay?
Well, okay.
Well, no, why not? What's wrong?
Because we had one.
And it was ours.
Yes, it was ours.
There's only one thing wrong with this picture. They're not squares. That's why I suggested closing your eyes and making them squares. What did you see when you closed your eyes? I saw you close your eyes.
I'm trying to see it then.
It's like they pull in two different directions at the same time.
Yeah.
I see it. Can we?
They pull in 2 different directions at the same time, rather going back to your ratios thing. How do you do that with numbers? How do you let the eagle of algebra come down and rescue geometry?
Very careful.
Yes. What if you assign the side length x to one of those rectangles, but both sides of it, and y to an adjacent one? For example, what if you, this is an arbitrary, what if you let E be x by x and H be y by y? What
E by
then
E and
happens?
each
So
side.
f must be f by x by y, x plus y by x.
Right. Sorry, which rectangle are you talking about?
F to the right.
Right. Then F would have to be x plus y. And B?
2x plus
B
1.
should,
Yes.
2x plus
Are we going to get x's and y's for all these rectangles?
Could be.
Probably not.
We could have a clash.
We'll get a view, but on the
Why don't we start with the small one? I want to start with D being x.
No, if you start with the B, then what?
Let's start with the little one, D being x.
It doesn't make
The little one D?
Yeah. Start with that being x. So we can add instead of subtracting when we get bigger things.
Fantastic. So all of a sudden it turns out our problem was looking at it with our visual eyes instead of our mental eyes, looking at it geometrically instead of algebraically. All of a sudden, algebra turns out to have a real value, which is important to 8 to 10-year-olds who don't see any point in it at all. I mean, the problem still may not be doable, but at least we've got some sort of hope. So if E is x by x, and H is y by y, then as you said, F has got to be x plus y by x plus y.
Which means we can get
So we
B.
know B and I now.
We
B
can get
must be double x plus y and I must be x plus double y.
Yep.
And I down there. X plus double y.
So,
And then G is
G.
going to be x plus
Yes.
G has got to be x
Have
plus
some.
y.
Okay.
Again, we didn't make enough.
and now we've got a problem.
What?
Yeah, we can't infer it.
I don't want to see.
How long is this?
2x plus 3x plus 2y, 4x plus
4x plus 4.
4y. No. So the horizontal is also for, no, it's not.
What did you get for D? If anything yet?
We don't have the.
Don't have D. What about?
let's let D be Z. Let D be Z, and we'll have 3 variables. We'll figure it out.
D's the hard one.
It
Let
would
it
be
be
really
Z.
nice if we could do it in 2 variables.
Are you resisting suggestions from the audience?
But the whole thing is not a square, no.
Right, he's got one. He's got one.
Name it, say it.
G what? Again?
DEF.
D, E, F.
These four lines.
It's already, yeah.
So D is, I heard it, 4Y.
4y, terrific. D is 4y. Could you explain your reasoning again? I'm not sure everybody heard it.
GI,
All the way from here to here is the
GI
same
is
as
2x
all the
plus
way
5y.
from there to there. And from there to there is 2 X's and 5 Y's.
and the other was 2x plus 1y,
Okay, now
and
it's easy.
4y.
Well, why is it easy?
Because, I mean, we can fill in the rest.
Okay, fill in the rest. What's A?
That would be x minus 4y.
Let's do C is x plus
Oh,
7y.
get C. What's C?
X plus 7y.
X plus 7y.
That's easy.
And now we've got A.
Okay.
Interesting that you have to go in a certain order.
Plus
X
11y.
plus what? Plus 11y.
Plus 11y. Now what?
Well, we have to
Let's compare
check
top and
them.
bottom.
We have
They've
to
got to
check
be the
them.
same, right? Okay, top is 3x plus 12y. And the bottom is 3x plus 12y.
Well, that doesn't give us much information, but it's encouraging.
So yeah, all the across is added to 3x plus 12y.
You want to do the sides? Or is it hopeless?
We did this one. This one is going to be 2x plus x
So
plus
y
x.
has to,
Give us
x
4x.
has to be 7y, so you can get all that's one.
So we're done.
Should get a
No,
contradiction.
2x on the left is 2x plus 18y.
Sorry?
Then you have to check the
Yeah,
normal
on the left,
actually.
right there, 2x plus
So look,
18y.
Joshua was suggesting that we do the sides. We get
2x
We have
plus
4x plus
18.
4y, and we get 2x plus
18y.
and they have got to be the same, those two side lengths.
So x is 7y.
So x is 7y. And therefore, you solve, let y be 1.
You can let y
And
alone.
then we will now get some equal sizes.
And they did, I think they all came out distinct, at least when I did the so it looks okay.
And that's a wonderful place, I think, to stop.
Yeah.
We've got to say a couple more things.
All right.
First of all, it looked impossible. It turns out to be possible. In this case, with a 9 tiling, we forced a card on you. We forced the 9 tiling on you. There's a lot of open problems here. One problem that's been solved is they can't be done with fewer than 9. Not clear with which rectangles it can and can't be done. All possible cases for 9 through 15 tilings have been done. There are 3,676 tilings, I believe, in that range. There's a lot that's not known. What about tiling an equilateral triangle with non-congruent equilateral triangles? What about tiling of 45, 45, 90 right triangle with non-congruent 45 by 45, 45, 90 right triangles? What about isosceles triangles? What about filling a box, a rectangular box with non-congruent cubes? The directions are endless. The answer to that one, by the way, you'll have as you walk out the door, I think. What's happened in the class with the 8 to 10-year-olds, and I hope with you, is that you see, first of all, the incredible power of algebra to come and rescue geometry. That what looks utterly hopeless is hopeful if you take a weird, imaginative approach. If you shut your eyes and see it with your eyes closed. That line about the eagle of algebra, by the way, is Sylvester's, the great English mathematician. And you were all fantastic, the way kids are. I mean, you were incredibly imaginative. Do this with your kids and let them hunt around, catch the frustration before it boils over, and let algebra come to the rescue.